Hey peeps, we're going to discuss more electrical circuits. This time our case study is the parallel circuit. It's really just as fundamental and simple as the series circuit, but it's going to take a little longer to describe only because there are some interesting sections with Ohm's law that we need to look at to really understand why the computation for R total is so weird looking, okay? So, electrical circuits, the parallel circuit. What we have here is a parallel connection of R1, R2, and R3. All right, and one thing we notice right away is that there are multiple paths for current to flow. So if I were to take one of these away, the current still flows, the circuit still operates for the other element. So if these were lamps, I'd remove the second one, the first one and third one still function. Okay, so it's very different from the series circuit in that case. They all have unique connections to the voltage source. And so with multiple paths of current, voltage happens to be the same for every element. They are, again, independently connected. VR1 has a unique connection to the source and a loop as well. VR2 has a unique connection to VR source. VR3 has another connection to V source. So it receives energy that's the same voltage across each of these. They are all in electrical contact. We see these parallel rails there, and these are parallel as well, and that's where it gets its name. And so with a loop analysis, we see that V rise equals V drop because it's directly connected to the source. Well, what does that mean? If I go up here, my rise is V source, my drop is VR1. They have to be the same because the rise is equal to drops. That's the conservation of energy per unit charge. If I look at it from this perspective, if VR1 happens to be the same as V source, I do the loop over here. This is a rise according to this loop. This is a drop, VR2. VR2 has to equal VR1, and the same logic goes over here. VR3 equals VR2 from this loop over here. And you can do a giant loop all around as well. There are many loops you can do. There are actually at least 2 more loops that we could consider for this circuit, and they'd all equal V source. All right. I total is IR1 plus IR2 plus IR3. The current splits. I'm going to redraw the circuit in the next panel that would illustrate this a bit better, so you can really see that there's a junction and that there's a flow of current and that it splits off into other resistors. And so it divides and comes back, rejoins. And then the R total is this weird thing over here, 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. That's a strange thing. The end result is that the resistance goes down, and why that happens is because the resistance divides among these. These may not be equal in reality when we study circuits, but if we think about these as being equal for the moment, let's set R1 equal to R2 equal to R3, what happens is that the current divides amongst the 3 resistors, and the total resistance is 1/3 of the single resistor if they were all the same. If they're not, you have to use this expression over here. And so in English, that's a strange little phrase, the inverse of the sum of the inverses. That's what it is. So the next panel, we're going to see how we get that. And we're also going to look at that junction split with a different diagram that's just as valid to represent the parallel circuit. Ha! You thought it was me. You did. Not me. Don't know who that was. Continuation here of electrical circuits, the parallel circuit. What I wanted to show is something called the conservation of charge with a parallel circuit. I've redrawn it to illustrate the fact that charge doesn't appear or disappear randomly. It all just flows through the conductor, which usually are a set of wires, copper or something like that. So we've got our V source, and now this is a parallel circuit, same one as before. What I've done is drawn it a little differently with a definite junction over here. This node is where I total goes in, and what it does is it splits, and it splits, and it splits between resistor 1, resistor 2, and resistor 3, and then it recombines at this junction, and then moves through the source. So you can see that there's a split of the current, but if we do the conservation of charge, we can say that I total has to equal the sum of the currents exiting. So the I entering, I total equals I leaving, which is IR1 plus IR2 plus IR3, okay? Current entering equals current leaving. In this case, current entering equals current leaving. The I total is the one that's leaving out of this junction over here. Okay, so that's how that works. Now, what about that funky looking resistance equation for R total on the parallel circuit? Here it is. Starts with Ohm's law. We got R total. And R total, as we know, is V over I. V total over I total if we rearrange it to solve for R. Okay, well, I total from up here is the sum of the current branches, IR1 plus IR2 plus IR3. And here we go. I just didn't write the R's to keep it a little simpler. So I1 is V total over R1, I2 V total over R2, I3 is V total R3. Why is this V total? Because in a parallel circuit, all the voltages are equal. Okay, so this voltage has to be V total over here. All right, so now what we do is substitute this in here, I1, this expression in there, I2 in there, and I3 in there. And what we get is V total over R1 plus V total over R2 plus V total R3. Notice that each term has a V total, so we can essentially divide by V total everywhere, and we just are left with this. Our total is 1 over R1 plus 1 over R2 plus 1 over R3. So in actuality, the resistance of the parallel circuit is independent of the voltage of the current, just like it is for the series circuit. So for any configuration, it won't change. You can change the voltage, which would mess around with the current. The resistance stays the same. But that's the case for every parallel circuit and every series circuit, okay? So this is how we come up with the funky R total, and that in total is our parallel circuit. All right, in another video, I will describe the series parallel combination circuit and a little bit about how to analyze it. It's a little trickier, but really fundamental stuff to know to combine these two packages together. All right, Morad out.